All right, so we're starting unit 4. Slowly but surely, we're plowing through it. Funky some days, but we're managing, and we'll get there in the end. Unit 4 is on chemical reactions. That is the title of the unit, which is kind of hidden in the unit pack. People at home, I hope you have the unit pack. If you don't, again, I sent an email out this morning. The sheets are on It's Learning. If you have printing capabilities, you're more than welcome to print. Otherwise, stop by the high school and come grab what you need. They are still on the first floor, pretty near the front office. So somehow, some way, make sure you've got something to stare at so you realize what I'm referencing. But like I was saying to the people here, if you heard me, Unit 4 I think is going to be better for a couple reasons. One, there's a decent chunk of review from last year, and two, I think it's just there's less of the weird conceptual stuff. You know what I'm saying? Like we've done a little bit of like orbitals and quantum mechanics, and that conceptually gets kind of obscure and annoying and confusing. And we've done like, I don't know, even intermolecular forces, right? It's kind of this obscure concept that we are generally trying to understand, and it's related to partial charges and Coulomb's law and all that kind of stuff. Very conceptual, and it can get very confusing. I think this stuff is also conceptual, but I think it's much more logical, much more like surface level. You don't have to dig deep for like these explanations. I think it's just a little easier. So I hope you like Unit 4. Unit 5 is a complete curveball, so we'll deal with that when we get there. It's its own topic. Unit 5 can literally be taught the first unit of the year or the last unit of the year. It wouldn't matter because it's literally like an island, is what I call it. It's its own separate concept. It's related to chemistry. It's a part of chemistry, but genuinely it could fit in anywhere throughout the entire year, and it wouldn't matter because it's not really tied to too much else. So anyway, all right. So today we have two topics: 4.1, 4.2. 4.1 is extremely short. I've got a couple definitions for you, and then we'll literally just jump into 4.2 because this is not too exciting. So let's go. Physical change. What is a physical change? Well, here's my definition. Okay. My definition of a physical change is a substance that undergoes a change in properties, but not a change in composition. I'll let you jot that down. Okay. The next one, assuming everyone's ready. Chemical change, which involves a change in composition. So a substance is transformed into a new substance, different chemical composition. Okay? This is very important. I will use chemical reactions to distinguish between these, but you're familiar with this. I think you probably talked about this kind of stuff in middle school, I would assume, right? Physical and chemical changes. We'll review just a smidge in the next couple slides, and then we'll just transition into the next topic. That's all 4.1 really is. It's just a recap or a revisiting of physical versus chemical.
Are we going to get to do chemical reactions?
I would love for that to be the case. Here's the hard part. And I've said this a little bit, but the only day it would really work is Tuesday. Because Tuesday is when we're in the chem room. Can't do a lab in here, right? I mean, can't do a lab upstairs in the IMC flex room. 238, we maybe could, but I don't want to set up crap in somebody else's room and leave it. So I will try to do something on a Tuesday with you guys, at least a couple times, because I think it is important. But yeah, I don't know. So, makes me very sad, and I'm sure it makes you sad too, because that's not the whole point of chemistry. So, anyway, we'll try. Okay, what are some examples of physical changes? We'll just start listing some random things. Yeah. Okay, freezing. What else? I don't know, I'm switching color mid here, but whatever. Melting, going the opposite direction, right? Instead of from liquid to solid, you're going solid to liquid. Yeah, sure. What else? Boiling. Condensing. Pure. Related to boiling, right? That's, like forced phase change versus spontaneous phase change, right? Kind of thing. Slight difference there. What else? The fun phase changes? From gas to solid or solid to gas? Solid to gas is maybe the one you know. Yep. Yep. Sublimation. Okay. I can't imagine you know the other one. Going from a gas to a solid. That was more.
About it.
Yeah, it's more obscure. It's called deposition. Okay. I've actually done it once in college, but yeah, it's kind of.
How do you do that?
So what you do is you generally have, it was in a vacuum chamber, so very, very, very low pressure, and effectively we just had, I don't even know how the heck we did it. So we had some gas trapped in this vacuum chamber and like a super cooled like piece of glass like in the middle there. So then effectively like the gas that was in the chamber just started like depositing and growing crystals on the super cooled piece of glass. Kind of cool. They're big, beautiful, like white crystals we were growing. I don't know what the heck, I don't remember what it was, but I don't know. Yeah, it usually involves some sort of like setup where you're really controlling the pressure or the temperature.
After it all, like in the natural world?
I mean, sublimation in theory, but here's the hard part. Like, you need, in order to have the solid substance that actually will like sublimate, right? You have to like cool down whatever the heck that was beforehand. So dry ice. Dry ice is the classic sublimation example. Dry ice is solid carbon dioxide. So if you have solid carbon dioxide out at room temperature, it doesn't matter. It literally goes from solid to gas. So you can buy dry ice too. You can just go to like the welding store over on, not Highway 29, but it's right off of Highway 29, American Gas and Welding or whatever that is over there. They have a little store. You can go in and bring a cooler or buy some dry ice. Kind of fun stuff.
So what temperature is it liquid at?
So it would have to be a different pressure. So under standard atmospheric pressure, dry ice does not melt. It will sublimate.
And that's why it doesn't.
Right. Yep. So if you change the pressure, I would assume you'd have to go probably higher pressure thing. There's a graph called a triple point curve where you look at the three phases of matter, and there's actually a point where like if you have the perfect pressure, perfect temperature, you can have all three phases of matter at the exact same time.
Oh.
That's weird.
It's really cool. You can do it with water actually,
Like just floating ice in the water.
and it's boiling. Yes.
What?
Yes. This is a real thing. Well, it's later in this unit. I'll show it to you.
You just gotta stick some ice on stuff.
No, it's so like it's the way that the one YouTube video I have embedded in that lesson. They have a petri dish, and there's like a layer of ice on top, and it's boiling, like bubbling underneath the ice, and like it's weird. Yeah, it's the weirdest thing. Anyway, okay, we're way off topic now, but I appreciate the questions. That's fine. Sorry, people at home. These are all the standard phase change things. We can have physical changes in other ways too, right? Like, for example, you can, like, I'll use just paper, right? You can rip paper, you can smash paper, you can do whatever. That's physically changing the appearance, but you're very clearly not changing it from paper to a different substance, right? So you can also physically manipulate things to get a physical change too. Chemical changes, what are we looking for? Okay, what are observations that we would make to maybe give an indication that something chemical is happening? This is the old middle school, right? Color change, sure. What else? Yeah, that's the best one, I think, right? Fire. Something's burning, it's chemical change. Okay, chemical change for sure. Bubbles. big three, really, right? We could do precipitation. That's pretty specific, but precipitation is when you take two liquid solutions and you mix them together and the solid forms. Okay, that's more of a specific chemical reaction, but that's one you could look for. I don't know. That's pretty comprehensive. You could maybe say odor, right? But generally, we're not. Most things we're producing or in the lab aren't going to be too stinky. Sometimes they are, but that's kind of more obscure too. But yeah, I think these three are the big ones, right? Something changes color, pretty decent indication that maybe a chemical reaction has occurred. If you got fire, yep, that's a chemical reaction, guaranteed. And if something's bubbling, again, you got to be careful because very clearly you can boil a pot of water and it's bubbling, not a chemical change. But if you're mixing things together and it's bubbling, that's most likely a chemical change. All right. That's it. 4.1's done. It's literally that is it. We're just kind of revisiting. Yeah, that would be nice. We'll ask probably one question about it on the test of Unit 4. It will. And it'll be nice and easy. But yeah, some topics, I think AP did a pretty good job organizing this class. I really do. Like their units are very, I think, structured pretty well. The structure of the whole year is pretty logical. But there's a couple of weird spots where it's like, again, we've spent 5 minutes on one section, and I've spent 4 days on one section as well. You know what I mean? Like, it's very strange how, like, they think that some topics deserve its own section. It's like, yeah, I can talk about that in 5 minutes, and you get it. In other sections, it's like, that's one section I need a week. And I don't know. So, anyway. All right. 4.2 is net ionic equations. We have talked about this a smidge. Okay, we did do maybe a couple examples of this throughout Unit 1 and Unit 2, but I never explicitly taught what net ionic equations are. So let's get into it. There's kind of a breakdown of the objective. That's at the top of your page, or maybe in the middle of your page. I forget where I have that, but let's just go through some different examples. We'll talk about what a net ionic is, and we'll just practice some problems writing out net ionic equations. Write a reaction for the boiling of water, physical or chemical change. Well, I think you already know this, right? It's physical. Here's how this looks. H2O going to H2O. This one is liquid. This one is gaseous, right? That's all we're doing. Now, if I want to be more complete, I could add energy. We have not talked about energy in terms of like chemical reactions and where the energy shows up. But let's think about this. If you want to turn liquid water into gaseous water, where should we put the energy term? Okay, think about it. Would we need to have energy on the reactant side, meaning liquid water plus energy is going to give us gaseous water? Or would we want the energy on the product side, meaning when we turn liquid water into gaseous water, we get energy release? I agree. We need energy over here, right? A little bit. We'll talk about it a whole heck of a lot once we get to Unit 6, okay? But energy needs to be added to turn your liquid water to a gas, right? When you're, mac and cheese is my classic example, right? You want to make some mac and cheese, you put a pot of water on the stove, turn it on, that's your energy. You're adding energy to that liquid water to turn it into a gas. Not the purpose of making the gas, but to boil your water, right? So, yeah, you need energy here. Physical change. Write a reaction for the burning of propanol. Not that I would expect you to know that that is propanol, but that's okay. Let's do this. When I burn something, what's the other reactant? No, that's going to show up on the other side. What's the other reactant when you have combustion? It is. We need some oxygen. After it's all done burning, one of the products is, Eddie, carbon dioxide. And the other product is combustion. You burn some carbon compound with oxygen gas, you get carbon dioxide, and you get water. That's ugly. Not that neat, right? It's pretty, but whatever. Okay, is this balanced? Not even close. Have fun. Good. It's all you. Try and balance it just for fun. This is what they're doing in general chemistry right now, by the way. They literally were doing this today. And they were succeeding, so hopefully you succeed as well. It's not necessarily an easy one, so hang in there. Where I think we're starting, right? Assuming I can count, hopefully. Now, it's been a while, but the advice that I always gave when I taught chem, I didn't teach you guys last year, unfortunately, but the advice I always gave was leave hydrogen and oxygen to the end. Do every other element, and leave hydrogen and oxygen until those are the last two. So carbon's not balanced. Let's fix that first, okay? I'm going to throw a 3 right here. And when I do that, I've fixed my carbons. I've got 3 and 3. But I've also changed my oxygens. I now have 6 plus 1 is 7. Okay. I'm going to go to hydrogen next, I think, because oxygen is literally in every single compound. That's annoying. Let's deal with that last. I have 8 hydrogens. I have 2. Let's fix that. And now I have 6 oxygens plus another 4. It gives me 10. Now, I want 10 oxygens over here. Do I want to change that? No, that messes everything else up. I don't want to mess with that at all. I would love to just fix this one and make it all work out. But currently, I need 10. I have 1 right here, which means I need to get 9. Right? Remember that whole 0.5 thing we did last year? Okay. I need 9 oxygens from this compound. If I put a 4 there, it's 8. If I put a 5 there, it's 10. So I'm going to use 4.5. When I do that, I've balanced my equation, but I can't leave it, right? Got to completely fix the whole thing now. So I multiply the whole thing by 2, and I get, here, let's go like that. I'll switch colors one more time. Orange. Getting really colorful today. 2, 9, 6, and 8. Just for fun. Physical or chemical? Chemical. That's combustion. You're burning stuff. Okay. So now, again, we can go through the definitions I gave you, 20 minutes ago, right? Physical changes don't change what you have. I've got water. I've got water. Same composition. That's a physical change. Chemical changes change what you have. I have propanol, I have oxygen, and that is now changing into completely different substances, carbon dioxide and water. Okay? I think you know all that. That sounds like all review for where we're at in our science, but just making sure, right? Let's keep going. Write a reaction for sodium chloride dissolving in water. Physical or chemical? This one's a little more thinky. Oh, it's just hit up the whole rainbow today, I think. It'll sound good. I have sodium chloride, solid, salt, table salt. And when you dissolve something in a solvent, like we are in this problem, the water isn't actually involved in the process at all. What I mean by that is, the water is the water. It's never going to change. Sodium chloride and the water aren't actually like chemically reacting whatsoever. Okay, so I'm not going to write water in on the reactant side at all. But what I am going to do is when I write salt on the product side, I'm changing what it was as a solid to aqueous. Okay. Did you guys do the whole aqueous thing last year? You know what AQ means, right? I hope. I forget where March was in the curriculum. I don't know. You guys did all the solutions and molarity stuff, right? Cool. So aqueous means something dissolved in water. Now, this is what's going to bring us to net ionic equations in just a second. When ionic compounds, because sodium chloride is ionic, we all know that, right? When ionic compounds dissolve in water, they don't exist as full molecules. They break apart. They dissociate. So this is an okay way of writing it, but in reality, when this dissolves, solid sodium chloride, when it actually dissolves in water, it doesn't exist as that molecule anymore. It exists as separate pieces, separate ions. So really, I'm going to rewrite this one more time. What I get are sodium ions with a 1+ charge, aqueous, plus chloride ions with a 1- charge, aqueous. This is a better way of writing. Okay? When ionic compounds are dissolved in water, they dissociate. I think we should write that down. I don't know where. You don't have as much space as I do. I apologize. Find a margin. When ionic compounds dissolve in water, they dissociate. Now, I will use the word dissociate or dissociation. I'll try to use that word only, okay? So you need to know what it means when I say it. It means break apart. Pretty simple word, but I'll try to use the actual term when I talk about it, okay? So salt compound, I put it in water, it breaks apart. Physical change or chemical change? It is. But do you see why it would maybe be confusing? Is this the same as that? Kind of no, I don't know. Okay, here's the deal. And there's a little bit of debate whether this is physical or chemical. At the end of the day, if I have salt water, or if I take salt, put it in water, and I make salt water, I can then take that salt water, boil off all of the water, and get my salt back. So this is a physical change by definition. Even though when we write it out, chemically speaking, or with the equation, it's a little confusing. But yeah, we're going to call this a physical change. Okay, we are going to call this a physical change. All right. So when writing out chemical reactions, there is sometimes more than one way to represent the chemical process that's occurring. When using chemical reactions that involve dissolved ions, as we just looked at, okay, and there's a whole bunch of ways and a whole bunch of chemistry that occurs with dissolved ions. I have some examples there. It's better to write net ionic equations when we have ions, aqueous ions in our chemistry. And aqueous ions, meaning ions dissolved in water, are extremely common from here on out. Okay? We're going to spend a lot of time looking at various reactions that have dissolved ions in solution. Okay? So more often than not, and what AP really likes you guys to do, if you can, is write a net ionic equation instead of a normal equation. And we're going to go through the process of how that looks and what that difference is right now. Not right now. Soon. Net ionic equation is this. It's a chemical reaction that only includes the ions involved in the chemical process. In other words, any ions that don't actually change, or any ions that don't actually do anything in the chemical process, are crossed off or they're ignored when we write out the reaction. How we doing? Okay? Hanging in there? Just think, 2 weeks from now, we're not here. We're all getting ready for Christmas.
Let's go.
Are we doing a final?
I'm not.
For what?
A final. I'm not doing a final. That sounds dumb.
Yeah, I was talking to
I
someone.
don't know. Just spitting some truth. I don't like it.
Yeah, because how are we supposed to do it? Like, it basically just be like taking a test.
Yeah, I don't want to do that. Do you want to do that? All right, good. We're all in agreement. No final. No, so the school itself is not organizing time for finals, but they're leaving it up to the teachers if they want to or not. But I don't want to. So you're welcome. All right, so let's look at some of this stuff here. Let's try one. When aqueous solutions of silver nitrate and magnesium chloride are mixed together, a precipitate forms. All right, what I want is to write out a reaction for this. It's been a while, but in theory, last year you learned how to take names and write formulas from those names. That was like unit 1 of regular chemistry. So it's been, 15 months. But maybe that's still rattling around up there. You might need a periodic table. I would strongly recommend a periodic table, potentially, especially for those polyatomic ions from last year. Okay? But what is the formula for silver nitrate? What is the formula for silver nitrate?
Is it AgNO3?
Fine silver. I'm not saying it wrong. Fine silver, which is Ag. What's the charge of silver? 1 plus. Nitrate is a polyatomic ion. You look it up on the back of last year's periodic table, and what do you find? NO3 1 minus. So silver nitrate is AgNO3. So yes, you are correct. Sorry for scaring you. You were absolutely correct. Magnesium chloride. Find magnesium. When you find it, what's the charge? 2 plus. Awesome. What's the charge of chloride? 1 minus. If I want to make that a neutral compound, I need the pluses and the minuses to neutralize or to balance out, right? Every compound that we create with these charges, we want to be 0 when it's all said and done. That's last year old news. Okay, so I have aqueous silver nitrate. I have aqueous magnesium chloride, because they told me that, right? They told me they were aqueous. That's why I know that this is the correct phase. And I mix them together, and it says that a precipitate forms. Now, I don't expect you to know this yet. I will help you with this part. What we're going to do is we're going to flip-flop. This cation is not going to go with that anion. And this cation is going to go with that anion. They're just going to switch partners. It's a double displacement. Okay? So on the product side, we are going to get silver chloride. Silver is 1 plus, chloride is 1 minus, and it's going to be like that. I'm not going to put a phase here just yet. And we're going to get magnesium nitrate. Did you guys go through how to use the solubility chart on the back of your periodic table? You might not have. That thing.
Yeah.
Yeah, it's a little funky. There's a better one in the chem room. I'll show you it, and I'll give you one later this year too. That's just a little cleaner. But if you have last year's periodic table, and if you remember how to use that solubility chart, go through these. Which of these two is our precipitate? See if you can do it. You're supposed to start with the anion. I don't even know if I have one of those. Ha, I did. Nice. Still a tough one. Anyone confident? The AgCl is the precipitate. What does that mean, though? It's a solid. Yeah, so now I'm going to write solid. The magnesium nitrate is aqueous. It's soluble. If you look up nitrate on this chart, on the back of last year's periodic table, nitrate doesn't matter what it's with. It's soluble. Aqueous. Now, this is a perfectly okay way of writing a chemical reaction, but it's not the most accurate way of writing a chemical reaction when it involves ions and aqueous solutions. So instead of writing it like this, all of these are ionic compounds. This is ionic, that's ionic, this is ionic, that's ionic. All 4 of them. Instead of writing aqueous ionic compounds together, we really should write them dissociated, because that's actually how they exist. Okay? When you have silver nitrate in water, in solution, it doesn't exist as AgNO3 molecules. It exists as separate Ag1 plus cations and separate NO3 1 minus anions. They're dissociated. All ionic compounds, what did we write? We wrote something important. Where was it? When ionic compounds dissolve in water, they dissociate. Okay? That's absolutely true. So let's take all of our ionic compounds that are aqueous, and let's break them in half. Let's dissociate them in our chemical reaction. Too far. Okay? So this doesn't actually exist as that molecule. Instead it exists, oh, we didn't balance this thing, did we? Let's do that. It's not hard. Ready? Think we need 2 of those? And 2 of these. Boom. All right, good deal. We're done. All right, now let's write this up. Okay, let's dissociate it. And we can use those coefficients to help us. That's why I wanted to do that first. But let's dissociate this. I have 2 silver ions, aqueous, plus 2 nitrate ions, aqueous, plus 1 magnesium 2 plus ion, aqueous, plus 2 chloride ions, aqueous. That's going to give me my products. The solid stays together, right? The solid compound, this is ionic, but it's not dissolved in water. That is the actual correct formula for silver chloride in its solid phase. Yes?
Do you have to put the charge on the...
Yes, I do. I'm sorry. Thank you. Head teacher. 2 AgCl solid. That is what it is, because that's not aqueous like the other ones. It's not dissociated. The formula is exactly the way it's supposed to be. Plus magnesium 2 plus aqueous, plus 2 nitrate 1 minus aqueous. Oh. It's a lot more work, but that's the way it's supposed to be. This is a more accurate representation of the actual chemistry going on. Because this, again, doesn't exist like that. It exists dissociated. And same with the other aqueous ones. This is a better representation of the actual chemistry. But we're not done. This is a complete ionic equation, one that includes everything. We're going to make it a net ionic equation. All we need to do now is cross off the things that don't change. Silver. Silver went from silver 1 plus to silver chloride. It's different. It changed. Nitrate went from nitrate to nitrate. It didn't do anything. This is what we call a spectator ion. Okay? What's a spectator? Somebody's just watching. Okay, you went to the football game and you were a spectator. You sat in the stand and you watched. Did you play football? No, you were doing nothing. You were watching. That's the same thing here. These are spectator ions. They didn't do anything. They were there, but they didn't do any chemistry, so we don't care about them. Magnesium, did it do anything? No, it's also a spectator. It's magnesium over here. It's magnesium over there. It hasn't changed. Chloride did change. So what we're left with then is the net ionic equation. We're going to write it one more time. But this time we're only going to include the pieces that actually did chemistry, the pieces that actually changed. Sorry. Okay? So the net result of this, or the net ionic equation, is 2 silver ions plus 2 chloride ions gives us 2 silver chlorides solid. And that is the net ionic equation. Okay? Now, the hard part is if you go way back up here, right? When you read this, it says silver nitrate and it says magnesium chloride, but the end result looks like this. You know? This is the mental process I kind of want you to go through. Eventually, you're going to get really good at identifying spectator ions. You'll get so good at it that you'll just kind of know what they're going to be before the reaction's even done, before we've written anything down. Because there's a nice kind of little, there's a nice set of ions that are spectators very, very often. Okay? Nitrate, for example, is going to be a spectator almost always in these types of reactions. Heck, I'm going to go further. It's going to be a spectator. Okay? Sodium, when sodium shows up in our reactions, it's going to be a spectator. So there's a set of ions that just are consistently the ones that we're crossing off. So you'll get good enough where you don't even have to hardly think about it like this after a certain amount of time. But we're not there yet. Okay? Couple things. This is a little tangent. Then we'll come back to writing some more practice reactions. Where net ionic equations become difficult is when we dissolve chemical species in water that don't dissociate, meaning some things dissolve in water, but don't break apart. Ionic compounds, like we wrote earlier, absolutely break apart. They dissociate 100%, meaning for every NaCl I put in water, every single one of those is broken. Every single one. We have 3 terms here. Strong electrolyte, a weak electrolyte, and a non-electrolyte. A strong electrolyte is a substance that dissociates 100% in water. A substance that dissociates 100% in water. These are a couple of common categories. Now we'll get more drastic change there. We have ionic compounds. Okay? Strong acids and bases. We haven't talked about acids and bases yet this year. It's coming. Okay? We'll talk about acids and bases in this unit. But generally speaking, your strong electrolytes are ionic compounds and strong acids and strong bases. Okay? Those are the 3 categories that we, more than any other category, identify as strong electrolytes. Something that's a strong electrolyte dissociates when it's in water. Weak electrolytes. These are, or this is a substance that dissociates very little in water. Okay? Dissociates very little. Now, what does that mean? Well, generally speaking, this is like less than 5%. Okay? Somewhere in that range, give or take. Sometimes it's like 0.001%, sometimes it's like 6%. But generally speaking, it's small. Okay, less than 5 is a good kind of spot to define it as. So weak electrolytes, if I put 100 molecules of something in water to make it aqueous, 5 of them are dissociating, the other 95 are staying together as the full compound. Make sense? These are generally, for our purposes in this class, these are weak acids and bases. And again, we have not talked about acids and bases just yet, but eventually that will make more sense. What do you think a non-electrolyte is? There you go. Yep. Strong electrolyte, 100%. Every single molecule dissociates. Weak electrolyte, a tiny bit. Like 5% or less dissociates. Non-electrolyte, this is a substance that does not dissociate at all. Okay? I'm going to be lazier. No dissociation. Okay? 0%. An example of a non-electrolyte is sugar. Okay? If you take sugar, sucrose, and dissolve it in water, that entire molecule dissolves. It doesn't break apart. It doesn't dissociate at all. Okay? Sugar is a non-electrolyte. The whole molecule, when in water, stays together as the whole molecule. Every single one of them. None of them dissociate. So these we don't deal with as much in this class. We care a lot more about the other two. Okay? These come up every now and then, but the main example of them is sugar. That AP will use sugar as their example of a non-electrolyte pretty often. Okay.
If you boil water, sugar water down, like salt water with sugar, so
Yep, absolutely. Yep. When you boil water, if you like, I don't recommend it because it's not good for your cookware, but if you had a pot of water, put it on the stove, and just let that baby go until it was all gone, you would have some residue of random ions of whatever was in that water, right? Because again, tap water, drinking water, all of that water has something dissolved in it. There's generally going to be, sodium ions, chloride ions, fluoride ions, a whole bunch, a little trace amounts of all that stuff in your water. Yeah.
With salt and sugar, like, since sugar doesn't dissociate, like, what's the difference of what matters?
Or why does that matter, maybe?
Yeah.
So it doesn't really matter in terms of for life, but what it does do for us is it gives us different properties. If I have salt water and try to conduct electricity through it, it will do extremely well. If I have sugar water and try to conduct electricity, it won't. So it gives us these different properties, which is why these kind of have their different categories. So different properties come from the different electrolytes when they're in water. All right, let's see if we can get one more in. Maybe two more. I got 10 minutes. What's this say? What am I teaching? When working with ionic compounds that are being mixed, they will either be insoluble or they will dissolve and be strong electrolytes. Okay. This is important. Good thing I put this here. Let me go back. There we go. This was our example we had already done. Okay. If I go back up to the top, this is an important thing to think about. Ionic, aqueous. Ionic, aqueous. Is that ionic? It is. It is. Metal, non-metal. Ionic, aqueous. So here's the deal. Not every ionic compound actually dissolves. Most do. Okay. In this case, we had 3 out of 4 that dissolve. But when an ionic compound doesn't actually dissolve in water, it doesn't dissociate, right? It's still solid, it's together. But here's the deal. If a tiny little portion of this actually dissolves, whatever tiny little fraction goes into the water will break apart. That makes sense. So when an ionic compound dissolves, it's a strong electrolyte, meaning it dissociates 100%, always, every single time. But not all ionic compounds actually dissolve. That's more of a precipitation thing. We'll deal with that when we get to equilibrium. That's what this is saying. Okay, let's try another example. We're going to do some acids and bases because these get a little funky. Hydrochloric acid is mixed with calcium hydroxide. You know the formula for hydrochloric acid? HCl. HCl aqueous is mixed with calcium hydroxide. You know the formula for calcium hydroxide? What's the charge of calcium? Uh-huh. What's a hydroxide? Uh-huh. What's the charge? 1 minus. So if I want to make calcium hydroxide, I need to make sure that that's a neutral compound. Looks like that. Okay. When acids and bases react, do you have any idea what the heck we get? Remember? Might not have even told this last year either, though. Who knows? Probably not. All right, I'll say it. When acids and bases react, you get water, and you also get salt. Now, the term salt is any ionic compound. So you get water and you get an ionic compound. Now, the water comes from the hydrogen and the hydroxide. That's what neutralizes each other to produce water. The other chunks, the calcium and the chloride in this example, come together to make salt. And when that happens, these are going to be aqueous salts. They will dissolve. Okay? So the product of an acid-base reaction is water from the neutralization part, plus some soluble salt, meaning some salt that absolutely will dissolve in water. Now, there's a problem here. This is not an anionic equation at all, right? At a minimum, that should be dissociated, because we know that ionic compounds that are aqueous dissociate. But we got these 2 guys. We haven't talked about strong acids or strong bases. Did you guys talk about strong acids, strong bases, weak bases last year? I know you did a smidge. Look to after 4.9. After 4.9 in your unit pack, you have a sheet that looks like this. This is the exact same one you got last year. Just, I think last year's was like, oh, it's probably white. It used to be pink. I think we used to make different colors throughout our packets, but we didn't do it anymore. Okay. At the top, we have strong acids and strong bases and weak acids and weak bases listed. Okay. Now, a strong acid or a strong base is the same definition as a strong electrolyte. Something that is strong dissociates 100%. It breaks apart. HCl, strong or weak? Strong. Calcium hydroxide, strong or weak? Is that strong with a question mark? You can get rid of the question mark. You're right. Yep. They're both strong. What does that mean? Yep, and what does that mean? They dissociate. They break apart. So instead of writing them like this, you break them apart. Go for it.
You want us to balance it first?
Oh, probably. That's a good call. I just work here. I'm sorry. Yeah, let's balance it. Is that it?
Yeah.
I think so. Sorry, I don't do the whole, like, you know, the way we teach it, where it's like, let's write all these elements underneath and let's do numbers and all that stuff. I do them in my head. Because, I don't know, it's fun. You Do any of you do Sudoku crap? Maybe have you tried one of these? Some people like write like little notes in all the boxes. Nuh-uh, I don't do none of that. It's all up here. I just, I can rip through hard Sudokus real fast. I like it. I like puzzles. I'm nerdy. Sorry. All right. So, I got rid of the middle step, I guess, for you, didn't I? That's okay. I don't know if we need it. Let's break these apart. 2. Hey, when those break apart, right? Obviously, this is just 2 elements. Oh, what did I do?
I just wrote out the whole thing
Oh, you did?
instead of doing the, yeah.
Well, I was actually going to write out the whole thing too, and then just cross things off.
It's gone anyway.
Okay, well, I'm sorry. I apologize. I have H1 plus, aqueous. That's acid, right? H1 plus, hydrogen ions, that's acid. We also have 2 chlorides. And I have 1 calcium. And I have 2 hydroxides. And on the product side, we get 2 waters. Water is liquid. By the way, the only phase of matter that we dissociate is aqueous. If it is solid, liquid, or gas, it's together. It's the normal formula like you've always learned. Okay? But if it's aqueous, there's a chance we might need to break that apart. It just depends upon what it is. And then I also have a calcium ion. I'm going to run out of space here. And I've got a couple chloride ions. My AQs are getting ugly. I apologize. Okay. What hasn't changed from both sides? Let's look. Hydrogen ions, that changed. Turned into some water with the hydroxide. Chloride ions. They didn't do anything. They're there, right there. They're a reactant. They're a product. They're unchanged. Okay, they're gone. Calcium ions. They didn't do anything. So the end result, if you want to rewrite it, you're more than welcome to. You don't have to. But the end result here is 2 hydrogen ions plus 2 hydroxide ions gives us 2 waters. Now, here's where it's a little confusing. That looks like it can be reduced, right? So I have 2, 2, 2. But it must be 2, 2, 2. It has to be. Because these other ions are part of this, and their charges matter in the grand scheme of the whole reaction. So in other words, if I make this 1, 1, 1, I'm kind of using like a half of a mole of calcium. Even though we don't write it in the final reaction, it's still there, and it still matters, so we leave it as 2, 2, 2. All right, let's sanitize. Those of you at home, have a lovely day. We'll pick this up tomorrow. We just got a smidge to finish, and then we'll jump into 4-3. Bye, guys. Thank you very much for your attention. I appreciate it.